In this section, we're going to talk about polynomial and rational inequalities. And anytime you're working with an inequality, the solution is going to be either an interval or it's going to be the empty set in the case that there is no solution to it. So really the way I want you to think about these is when you're working with an inequality, if you get 0 on one side of the equation, you're really asking where that function is greater than 0, less than 0, or whatever inequality you're working with. So we're really going to utilize characteristics of the graph to help us solve inequalities. So before we get into if I just give you an inequality, how to solve it, we're going to look at utilizing a graph to solve an equation or an inequality. So starting with this first one, we want to figure out where 5 times x minus 1 squared times x plus 3 is equal to 0. So the graph of 5 times x minus 1 squared times x minus 3 is going to be over here. This is a polynomial that we know how to graph. It's got zeros at positive 1, and that multiplicity is 2, so it just touches there. You have another 0 at 3, and it's a multiplicity 1, so it crosses through. And if you think about the degree of this, it's x squared times x, so it's a cubic function. It's positive out front, so that means it's got the end behavior of down to the left and up to the right. So that gives us an idea as to what that graph has to look like. So if I want to figure out where this is equal to 0, that's the same thing as figuring out the zeros of the equation. So this one's not bad. It's something you could solve. The two values that make this equal to 0 are 1 and 3. But utilizing the graph, it touches the x-axis at 1 and 3. So in this case, our two solutions to this are 1 and 3. So this is the same as asking where f of x is equal to 0. So in this case, there are two x values that occurs for, positive 1 and positive 3. In the second example, we want to see where this is greater than 0. So that's the same thing as asking where the function is greater than 0. The thing I want you to recognize is that these two values where the function exactly equals 0 are important, because what can happen is that polynomial can cross through and it can go from negative to positive around to 0. Same thing here, there could be, if it didn't have that even multiplicity, a chance that the function went from negative to positive or vice versa. So these values where the function equals 0 are super important for us. But since I have the graph, I don't have to worry about solving this analytically. I'm just going to utilize where the function is positive, and that would be over here. And you want what x values it happens for. So we need to figure out where f of x is greater than 0. And that means the output of the function is positive. So this is the same thing as asking where the y is positive. So where is the function above the x-axis? And again, I want the x values that happens for. So this is where f of x is greater than 0. It can't equal 0 though. So the x values that occur, it starts at 3 and goes forward forever, but it's not equals 3 because it cannot equal 0. So my solution to this inequality would be from 3 to infinity. And then we have those open brackets around both because I cannot equal it. If I want to figure out where this is less than or equal to 0, this is going to happen when the function is below or on the x-axis because we can equal 0. If it was strictly less than 0, then you technically would have two intervals. You would have from negative infinity up to 1 with parentheses, And then you would also have this interval from 1 to 3. But because we can equal 0, 1 is going to work for us, and also 3 is going to work for us. So these are the values for which the function is less than or equal to 0. So it's starting at negative infinity and going up to positive 3. But again, if I made this stricter and said strictly less than 0, that would be from negative infinity up to 1, but you can't equal 1 because that's where it equals 0. And then also between 1 and 3. So it all depends on what inequality sign you're working with. Okay. But the thing to recognize are these two values, 1 and 3, are important. They're cutoff values where a function can change sign around it. So if I didn't know the graph of this, or it's something really complicated that I want to go through, instead I want to figure out analytically, how can I go about solving this inequality? The one important thing to remember, especially when we deal with the rational inequalities, is that you never want to multiply an inequality by a variable. The problem by doing this, if you think of if you have 1 is less than 3, that's a true statement. If you multiply this by -1, you would get -1, -3. The inequality sign has to flip to make it a true statement. When you're working with a variable, you have no idea if the variable is positive or negative because it's an unknown value of x. So in that case, when do you change the direction of the sign? You won't know. You don't know when it's positive and when it's negative. It makes it really messy. So you never, ever, ever want to multiply an inequality by a variable. Instead, what you're going to do is you're going to move everything to one side and you're going to find key numbers to do interval testing. So to go back up here to show you what those key numbers are, it's these cutoffs where it exactly equals 0. So if you got everything on one side, you're going to have 0 on the other. So you're finding these values where it's going to touch or cross through the x-axis. So in this case, if I was working with this inequality and I wanted to do interval testing, I would break that down as 1 and 3, and then I would go ahead and test each interval. If I picked a number over here, that would correspond to this part of the graph, and any value I picked that was in this interval would tell me whether the function was positive or negative. Then when you go in between 1 and 3, you're looking at this part of the graph. So if I pick 2, it immediately tells me my function is negative. So I know on that interval, it's completely negative. And likewise, when you pick something from interval 3, you'd be on this part of the graph. So it will always give you a positive quantity. So because you're picking those key values where it exactly equals 0, there's no way on that remaining interval that it's going to cross through the x-axis. So you're picking all the possible places where the function can change signs. Okay? So you always want to get your inequalities into a form like this where you have 0 and everything else on the other side to represent your function. Okay? So let's try an example of this. We want to solve the inequality and we want to state our solution in interval notation. So the very first thing I want to do is move everything to one side and factor. Okay. So I've got to subtract the 15. That gives me x squared minus 2x minus 15 is greater than 0. Okay. And I want to factor just to make my life easier to immediately pick off those key features. They should always factor nicely. You're not going to get something with terrible roots. But to get to negative 15, you have a 5 and a 3, one being negative, one being positive. Since I have more negative, we'll do negative 5 and positive 3. And if I go ahead and check, the outer is positive 3x, the inner is negative 5x. When you add them together, fantastic, you get the middle term. So that is fully factored. So if I were to graph this, this would be a quadratic. I could find the zeros for it, which is exactly what I'm going to do. I'm going to find the values that make this equal to 0, because that is where that quadratic can change signs and go from positive to negative. So our second step is we're going to find values that make the inequality equal 0. Okay, so these are the important numbers or key numbers, but it's not something that I have to set equal to 0 because it's pretty straightforward. If it was like 2x minus 5 needs to equal 0, yeah, you probably have to set that equal and solve it. But our two key numbers are positive 5 and negative 3. That will be where the quadratic equals 0. So if I were to graph this thing, it would go through positive 5, it would go through negative 3. It's x squared and it's positive x squared, so it's got m behavior like this. They are multiplicity 1, so my graph would look something like this. And again, I can utilize that to now see where this is greater than 0. It's going to be over here and over here. But again, we're going to do that analytically. So my third step is I'm going to create a number line. And I'm going to choose a test value in each interval. We're going to see if that value satisfies the inequality. Okay. So I'm creating my number line here with these key numbers, putting them in order. Negative 3 is here, positive 5 is here. And these key endpoints I'm going to put circles at. The inequality is going to tell you whether you can fill these in or not. Since I'm strictly greater than 0, these values are not going to work, okay? So I cannot fill them in. They are going to be open circles. And what this does is it splits my number line into 3 different intervals. What I'm looking for is x squared minus 2x minus 15 greater than 0, and we can't equal negative 3 and 5 because our sign is the strict inequality. We cannot equal 0. Okay. So I need to pick something from interval 1, and I'm going to see, does that work? And so I need a number here to the left of negative 3. You have freedom to pick whatever you want. Don't pick a huge number, but we'll pick negative 4. So I'm going to plug that into my inequality. You can plug it in here too. It doesn't really matter which one. If you use the original, it's just less likely you made an algebra mistake then. But again, completely up to you. I'll show you with both of these that they will work. But if I plug that in, that would be x squared minus 2x minus 15 needs to be greater than 0. Negative 4 squared is positive 16. Negative 2 times negative 4 is positive 8. And then minus 15 needs to be greater than 0. I don't really care about simplifying this whole thing. But if I do 16 plus 8, that gives me 24. 24 minus 15 is definitely greater than 0. I don't care what that actually equals. I just know it definitely works. So that tells me this whole interval works. So any number I picked, I would have gotten that. Okay. And again, that's because of what our graph looks like. My zeros are negative 3, 5. It's a quadratic. It looks something like this. Yes, over here is where my function is positive. So I should see now for the second interval, it's not going to work. That's where my function is negative. So if I pick something in interval 2, let's pick 0 because that's always really nice. You can pick really -2, you can pick 1, whatever you want. And I'm going to go ahead and I'm going to use this factored inequality to see if it works or not. So if I plug 0 into that, that would be 0 minus 5 times 0 plus 3 needs to be greater than 0. -5 times +3 is a negative number. Again, I don't need to actually multiply that out. Negative times a positive is not positive. So unfortunately, this interval does not work. So nothing I picked in there would work. And then last but not least, moving on to interval 3, I could pick 6. That's a relatively small-ish number. And again, you can use either 1 to plug it into. I'll go ahead and plug it into this one. That would give me 6 minus 5 times 6 plus 3 is greater than 0. 6 minus 5 is 1. 6 plus 3 is 9. Positive 1 times positive 9 is definitely greater than 0. So interval 3 works just like we imagined from the graph. So to write our solution, we do need to write this in interval notation. My first interval goes to the left forever. So it's from -infinity up to -3. And I cannot equal it, so I put that parenthesis. And then also interval 3 works, so we use our union symbol. We start at 5 and cannot equal it, and then go to infinity. So that is our solution. Okay. So all your polynomial inequalities are going to work just like this. You're finding those key values equal to 0. So to just kind of reiterate why we did that again, why did we move everything to get 0 on one side of the inequality? Why are we finding these key values where it equals 0? But we are essentially finding where the function or where that polynomial is positive, or negative if your inequality is finding where it's less than 0. So a polynomial can only change signs around a 0, which is why they were the important numbers. There's no other possibilities. So when we're now stepping this up and working with a rational function, it's still the same kind of idea. You can change signs around a 0. But the other thing where we can change signs around is with a vertical asymptote. So that's also going to be a key number for us. So ultimately, to give you just two kind of pictures, when you're working with polynomials, this is the only case that your function can change signs around a 0, because that's where it can go from negative up to positive. And same idea with a rational function, it can change signs around a 0. But also if you think about your vertical asymptotes, if I have a vertical asymptote, say here, and let's go ahead and make that dotted, so it actually looks like an asymptote. Your graph could look something like this. It could be negative to the left of the asymptote, but then it could be positive to the right. So it can also change signs around a vertical asymptote. Okay. And with a rational function, these values are where the numerator equals 0. These values are where the denominator equals 0. Here, there was no denominator, you just had 1, so you were just finding where the numerator equals 0. So it's the same idea. You're going to get everything to one side, so it's greater than 0, less than 0, whatever it may be. And then you're going to find these key numbers by setting the numerator equal to 0 and setting the denominator equal to 0. Okay, so again, this is just where the numerator equals 0, and those vertical asymptotes occur where the denominator equals 0. Okay. So we're going to start with one that's real messy. And if we can do this, we can do everything. The second one will be a little bit easier. But we've got this really messy rational inequality. And I want to find the x values that make it true. So the very first thing is I'm going to move everything to one side, and then I'm going to get a single rational function on one side of the equation. So here we move everything to one side. And we condense it to a single fraction. So it is going to take some algebra for us, but that's okay. All right. So we've got negative 2x minus x squared over 4 minus x needs to be greater than or equal to x. So if I move that to the other side, we have to subtract this. You can put it at the end. I'm going to go ahead and put it at the beginning, though, just because I've got to condense these things. So we've got negative x plus this expression. And now we have greater than or equal to 0. And again, I want to be able to add these together so I can immediately pick off my intercepts and my vertical asymptote. So I need to make this have the same denominator. So I need a 4 minus x in the bottom, which means I have to do exactly the same thing to the top. So I really need to multiply this by 4 minus x over 4 minus x. So I'm going to wait to kind of condense everything. We've got 4 minus x times negative x over 4 minus x. And then we're going to add 4 minus x in the bottom and negative 2x minus x squared in the top. Okay. I like to wait to multiply stuff out because these minus signs can be a pain in the butt and really easy to drop. So I like to make this one giant fraction before I multiply stuff out. So I'm going to put that negative x in the front just to make life a little easier. And then we're going to add it to this other expression. And again, I just really like doing it this way because if this was minus, the number one mistake that happens is you forget to distribute the minus out to both things. And if there was like a 3 out front I needed to be able to add these fractions together for whatever reason, you then would remember the 3 has to distribute to everything in that numerator. Okay. So now from here, I can go ahead and I can distribute this out. So if I distribute that negative x, that's negative 4x. Then we get plus x squared. And then dropping that plus sign, because it doesn't do anything, we get negative 2x minus x squared over 4 minus x. And then thankfully, at least one nice thing happens. We have plus x squared minus x squared. Those are gone. Negative 4x minus 2x gives me negative 6x over 4 minus x needs to be greater than or equal to 0. So I've now condensed this to a single rational function, and I'm finding out where this rational function is positive or equals 0. So if I go to now find my important numbers, I can do that right from here. So I need where the numerator is equal to 0. So if I set that equal to 0, well, that gives me x equals 0. And then when I set the denominator equal to 0, another key number is positive 4. So that's going to be how I break my number line down. We got 0, we got 4. We put open circles at them and we see, can we fill this in? But ultimately, again, I'm going to have 3 intervals to test. Okay. If I want to see what I can equal, I'm going to start with 4. That's where the denominator equals 0. So regardless of whatever this inequality is, I definitely cannot plug in 4 because that would cause 0 in the denominator. So this one will always be an open circle wherever that denominator equals 0. But for this value, this is where the numerator equals 0. So that's where you care about the inequality sign. And since it's greater than or equal to 0, we can indeed fill that in. Because the symbol we have is this one. Okay. Now I want to go through and I want to do my interval testing. This one, if you wanted to plug it in back up here, it would definitely be really messy. Just go ahead and use that condensed form that you have. It'll make life way easier. But I ultimately have 3 intervals that I need to test. So from the first one, let's pick -1 because that's not too terrible. So if I plug in -1, that would be -6 times -1 over 4 minus -1. We want that to be greater than or equal to 0. Well, -6 times -1 is +6. 4 minus -1 is 4 plus 1, giving me +5. I get 6 over 5. That definitely works. So that tells me everything in this interval is good. If I move on to interval 2, I can pick +1. That falls in there. So if I plug that in, that's -6 times +1 over 4 minus 1 needs to be greater than or equal to 0. Well, that's -6 over +3. It's greater than or equal to 0. I don't care that simplifies. A negative divided by a positive does not give me something positive. So interval 2 is no good. Moving on to interval 3, let's just pick the next number, 5. Okay. If I plug that in, that's -6 times +5 over 4 minus 5 needs to be greater than or equal to 0. That gives me -30 in the top, -1 in the bottom. And again, I don't care about simplifying this. A negative divided by a negative does indeed give me something that is positive. So interval 3 is also going to work. Okay. So everything from interval 1 is good and everything from interval 3 is good. So our solution, interval 1 is from -infinity up to 0. We can equal 0, so we put that bracket. And then we have another interval starting at 4 and going to infinity, but I cannot equal 4 because that causes my denominator to equal 0. So anything in these intervals will satisfy that original inequality. Okay. Now it might seem really natural, especially while you're going through and doing these things. You might think you notice a pattern that it alternates. Be really cautious. Even our next example is going to do that, but it is not always true. It depends on multiplicities of zeros. So to just kind of go back up here, for this example, if you look at this one, well, it's negative on this interval and negative on this interval, but if you were to split this number line up, those key values are 1 and 3. This one does not alternate into whether it's positive and whether it's negative. So be really conscientious. That is not a pattern that's going to happen. It always is going to depend on the inequality, okay? So let's try one more example. This one at least is a little bit nicer in that we already have 0 on one side. So fantastic, I don't have to do all that extra work of condensing it. So you can see that can take quite a long time. But what I do need to figure out is those key numbers. So I am going to have to factor that numerator. At least it's not too terrible. Again, these things should always factor. Otherwise, you've made an error somewhere in your algebra. To get x squared, we need an x and an x. -5 means we have a 5 and 1 with opposite signs. Since the middle is positive, we'll do +5 and -1. Just to check that out, -x plus 5x indeed gives me that middle. So if I look for my important numbers, I need where the numerator and denominator equals 0. Well, I've got -5, +1, and +3. Okay. And in this case, if I want to figure out what I can and can't fill in, I definitely cannot fill in at 3. But since I have that strict inequality, I don't have to worry about it all. We can't fill in anything. Okay. So when I go to create that number line, I'm going to have open circles everywhere. And now here I have more intervals I have to test. This splits it into 4 intervals. Okay. So a little bit more work to do. The other thing that can also happen is these numbers could be right next to each other. Like I could have made this x minus 2 in the bottom. When you have to pick something that's in between, just pick like 1.1 or 1.5, something again easy. And you're just keeping track of signs. You don't need to actually do division and see what the number is. Just, do you have positive in the top and positive in the bottom, negative and positive? What combo? Is it negative or is it overall positive? But I've got 4 intervals to pick. So starting with interval 1, we'll pick -6. Okay. And so if I plug that into that factored form, that's -6 plus 5, -6 minus 1, and then -6 minus 3, and we want this to be less than 0. -6 plus 5 is -1. Then we get -7 and -9 in the bottom. When I'm working with 3 negatives, it's overall going to be negative. So fantastic. This interval is going to work. Moving on to interval 2. Let's pick 0 because that falls in there. And I'm going to move these over because I would like to fit everything in on this screen. That gives me 0 plus 5, 0 minus 1, and 0 minus 3. Well, I have 2 negatives. That turns to a positive. So unfortunately, this interval is not going to work. Moving on to interval 3, you can definitely pick 2. But again, what I'd like to show you is if this was a 2, I'd have to pick a number in between those, and that would be a decimal. So I'm going to show you how to do that with a decimal, just for good measure. Okay. If I pick 1.5, that gives me 1.5 plus 5, 1.5 minus 1, and then 1.5 minus 3. And we want this to be less than 0. That gives me positive 6.5, positive 0.5, and negative 1.5 in the bottom. Again, do not care what any of this multiplies out to. Positive, positive, and then a negative. I have 1 negative. This thing is definitely overall negative. So it will work. And then finally, moving on to the 4th interval. let's pick 4 here. That gives me 4 plus 5, 4 minus 1, and 4 minus 3. We need that to be less than 0. That gives me 9 times 3 over 1. So this interval is no good. Okay. So just interval 1 and interval 3 work. So our solution is negative infinity to negative 5. Can't equal anything. And then also 1 to 3. Now again, don't do more work for yourself, especially if it then gives you a next part and it asks you, where is this greater than 0? Well, it's just going to be the other intervals then, because either the function is positive or it's negative. There's nothing in between. If it then adds this inequality where you can equal, then you just have to go back and look at your numbers. This is where my numerator equals 0. This is where my numerator equals 0. So all it does is change brackets on your solution, okay? So use that to your advantage. Don't sit here and go back through the entire interval and test everything again.